Welcome to Cassandra Lunch number 139. Don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. Today, we will be discussing LLM fine-tuning with QLoRA, focusing on evaluation. Our speaker is Obioma Enamnachi, and he will be discussing delving deeper into the world of LLM fine-tuning. This session, the third in our series, we evaluate the difference in performance between our LLM fine-tuned, our fine-tuned LLM and the original Llama 2 model. We have some mathematical metrics, and then we present the results of some performance evaluation that combined human and LLM evaluation. The co-organizers for this event are Rahul and myself. If you are interested in being a co-organizer and want to get help speakers by reaching out to people in the Cassandra community around the world, drop me or this marketing email a message. If you yourself are interested in giving a Cassandra lunch or speaking at our sister event, Data Engineers Lunch, please reach out to me through either one of these emails. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, generally centered around data, and you can find out more about all the various groups and events at datacommunitydc.org. What do we cover here at Cassandra Lunch? We cover all things that are, talk, and play well with Cassandra. We cover open source Cassandra enterprise variants such as DataStax, Scylla, Keyspaces, Cosmos DB, and Yugabytes, and the ecosystem of around those tools such as Spark, Kafka, Airflow, Airbyte, Snowflake, and so many more. If there is anyone new that would like to say hi, what brought you here, and what you hope to get out of this talk, drop something in the Zoom or YouTube chat. YouTube chat, that's where you're watching. And a few rules. If you have a question, please ask it. Obi prefers for me to ask questions when they come up. So put them in the YouTube chat and I'll pass them to him. Please be polite and courteous to others. And of course, share what you know with us. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. Cassandra is our bread and butter. We've also stepped firmly into the generative AI LLM space to deliver RAG chatbots, agents, prompt engineering, and fine-tuned LLMs for a variety of enterprise use cases. Thanks to all of our sponsors, including DataStax and George Washington University, where we have in-person events. Thank you also to all of our institutional and organizational sponsors. If anyone has any job offers, you're looking for a job, please feel free to put those links in the chat. If anybody has any meetups, hackathons, classes, or conferences that you'd like to promote, please put those links in the chat as well, and I'll mention them at the end of the session. We host Cassandra Lunch on Thursdays at noon Eastern. We are very open to changing our method of broadcast, so if you want us to do this at a different time, please let us know. Our sister lunch, Data Engineers Lunch, takes place Mondays at noon Eastern. All of Cassandra Lunches, starting with Cassandra Lunch 10, are available on the Cassandra Lunch playlist. We also have a new playlist focused on no-code and generative AI, where you can also find this specific video after it releases because of the topic of Obi's talk here. We also want to highlight Cassandra.link, a hand-curated site with resources for Cassandra by the team here at Anant. And finally, we have a series of Cassandra runbooks coming up to number 17 here. You can download the most recent one for free and get access to a lot of great Cassandra information on our site. With that, I want to thank Obi for being here, and I'm going to pass it to you.
All right, thanks, Nick. All right, so as you heard, today's topic is the continuation of our series on LLM fine-tuning. Today, we're talking about evaluation. So the first part was about what is fine-tuning and how do you build a data set that could potentially get you what you want out of it. And the second was how do you fine-tune with a focus on things like quantization, and memory management and stuff like that. This time we're talking about, once you have completed the fine-tuning process, how do you evaluate your results? So we're going to talk a little bit about how do you evaluate LLMs in general, and then how do you evaluate them in comparison with each other, in the service of comparing our fine-tuned model to the Llama 2 model that it's fine-tuned from. And we'll talk about the different ways that people use to do that. So this is the 5 types of evaluation we'll be covering today. First is domain-specific tests, also known as simulated exams. It's pretty self-explanatory. Basically, you do an evaluation for a specific domain. Usually this uses an existing test, maybe the bar or medical school exam, the SAT, etc. And the performance of the model on that test is used as sort of a benchmark. And the second is benchmarks, which are a series of specifically defined tasks and outcomes that are compared to the results against other large language models, or at the very least, other automated systems. So in domain-specific tests, you're comparing it to the performance of humans on that same test, or to an objective standard, like how many questions are correct or incorrect. Whereas benchmarks only make sense to evaluate in comparison to other benchmark values. Third is statistical measures. They are objective quantitative evaluations of the language model's capabilities. And then there is human evaluation, where you get your ratings from human evaluators who are looking at the outputs of the model. And LLM evaluation is basically the same as human evaluation, except it's being left to an LLM. So in the end, like Nick mentioned, we have some human evaluation on our models to compare the responses we get from our original model and our fine-tuned model. And we also have LLM evaluation here. As we go through the demo later, I also threw in one of the statistical measures, but we'll talk a little bit later. The one that we used is called Rogue, and it's only applicable to some of the things that we used our model for. So can only be computed on a subset of data. Okay, first type, like I said, simulated exams or domain-specific tests. If you look at the research page for GPT-4, which is where this chart on the right comes from, this is the first sort of capability thing that they want to show off. They have had it take the bar exam, the LSAT, SAT sections, both the reading and writing and the math section, the GRE, various sections of that. So basically, these are existing exams that they set up some systems so that the large language model gives responses to the questions on the exam, and it is then graded as if a person took the exam, and you're able to compare these. So you see they give estimated percentile, but also look at an objective measurement, how many questions are correct. Basically, all of these act within a particular domain. So LSAT is students potentially entering law school, SAT is students entering college, GRE, students entering graduate education, etc. Or medical knowledge self-assessment, AP art history, etc. So more domain-specific ones. It's sort of a test of the linguistic patterns, the vocabulary, and then also contextual knowledge, question answering ability, potentially reasoning ability if there are math questions, et cetera, et cetera. Second is LLM benchmarks. So the image on the right that we have here is correlation between NLL and accuracy on common sense QA benchmarks. So all of these different models here have been tested on the same QA benchmark, and then they're all graphed in order to compare them to each other. Basically, measure this performance of a model against other models or against other systems. So if there's a particular task that a model is doing that another system can also do, like potentially summarization models that existed before LLMs, can be compared to LLMs using those same benchmarks. Consists of predefined tasks and evaluation metrics that assess the capability of the model. Example, ABX task is about distinguishing between pairs of phonetically similar sounds. And then example 2, the closed test. There's a piece of text with certain words missing, and it's how well the model then fills in those gaps. So the results of this, they might still be individually subjective, as it needed to be rated by a human or LLM. But eventually what you get out is a benchmark that can be applied and then compared across systems. Statistical measures are objective quantitative evaluations of model output. So example 1, commonly used, is perplexity. There is a image on the right that I made for perplexity. It measures the sort of level of uncertainty or level of confidence that a model has when predicting the next words in a sequence. So because transformers generate words one at a time, this is generally pretty easy to calculate if you are in fact getting back your potential choices and probability back from the model. If you don't have that data and only have the text output, as with, say, if you're using ChatGPT online, or something like that, this would be harder or impossible to calculate without access to the internals of the model. So low perplexity or confusion means that a model is confident in its choice of next word, whereas high perplexity means that there are a bunch of potential words with lower chances of being selected. And so what this really measures is the model's confidence in picking words. And the issue with using this as a value for sort of the goodness of your LLM, like you would see a clear difference between, say, GPT-2 and GPT-3 in this regard. But what you're really measuring is the model's confidence and not in any sense like accuracy. So we've all seen models be confidently wrong about what word comes next in a sequence. The second example statistical measure is ROGUE, recall-oriented understudy for gisting evaluation, which I feel is it's a weird acronym. Mostly I feel because of the word gisting, but basically it analyzes summarization models. This is the one that we use. Some of the tasks that we set for our LLM are summarization tasks, and we can take the results of those and compare it to a reference summary. For example, the one that was generated as part of the training set, and compare that to the summaries that are generated by our base LLM and by our fine-tuned LLM. And then the last is BLUE, bilingual evaluation understudy, which is used for evaluating machine translation models. It assesses the quality of translated text by calculating the precision of n-grams or sequences of words against sequences of words in the reference translation. And then we have human and LLM evaluation. I've lumped these together because they are sort of the same. LLM evaluation is just trusting the LLM to do something that the human would otherwise be doing. Basically, you gather feedback or ratings on specific model outputs from your human evaluators or maybe from an LLM. And they provide subjective ratings or comparative assessments or task-based evaluations. And all of those are sort of different ways to sort of look at how you should rate model outputs. Subjective ratings is just this individual output from your LLM. How good is this in a subjective sense? So it uses like Likert scale evaluation or sentiment analysis of written feedback or something like that to determine this sort of ranking in a vacuum, just depending on what the human sees when they look at the output. And then comparative assessment is about comparing multiple variations of the output and rating them based on specific criteria. So this is rank ordering, choosing the better of two outputs, etc. Just whatever versions of the output you have, depending on, maybe they come from different versions of the model, maybe they come from different prompts, etc., etc. They're being compared against each other rather than rated in a vacuum. And then task-based evaluation is about using the model and providing feedback based on the task that you used it for. So this is an even more subjective because your response is given in sort of text format. It isn't exactly necessarily useful for numerical comparisons. All right. So we're going to
So,
move on
Obi, I
to,
did have a question about one of the things you mentioned in that discussion.
yes.
So if you go to the previous slide, you mentioned that perplexity tended to be more of a problem in GPT-2 from GPT-2 to 3. Can you talk about what has changed that GPT 3.5 and GPT-4 don't have these same issues?
So part of it is just basically the amount of data and the structure of the model. So transformers with attention and the fine-tuning processes that give rise to something like ChatGPT over GPT 3.5 means that it has a sort of better underlying statistical model of the language, which means it can be more sure what word comes next. So the words are still selected sort of randomly, but it's choosing from a shorter list of more appropriate words than a longer list of potentially less appropriate words. That's why GPT-2 would give non-grammatical and nonsensical output, but GPT 3.5 is less likely to do that.
Great. So it's another scenario of another set of layers really making the difference.
Yeah.
Yeah. Okay.
All right. So this is our repo. It has the evaluation code and the data analysis code included. So we are going to go through the LLM evaluation sort of process. So first, let's take a look at our evaluation prompts. They can be much shorter than the instruction prompts because what we're actually doing here is all we want to do is say, okay, this is the instruction, this is the context, this is the answer, rate how well the LLM generated answer fits the provided instruction and context. So is it actually answering the question? Is it performing the task? Rate that on a scale of 0 through 9. So looking at our actual code, we start again by connecting to our Astra database where all of our results are stored. So in that database, well, actually, I should start with the code that actually uses both LLMs and gets the response. So before this, starting at where we ended last time, what we have is a stored adapter, the QLoRA adapter. We have that stored. We have our original model weights stored. And then we have the generated data set in an Astra table. So the first thing we do is we load in our model weights and we load in our adapter. We put it in outputs last time. So we're copying back into the environment. And we set up our requirements, outputs, devices. We set up CUDA. We connect to the Astra database and get back all of our data. So what we have in the table at this point is ID, instruction, input, and output. And all of our instructions have that format. So what we do is we build a sort of incomplete instruction prompt. We have the output that GPT-4 generated in our first step, where we were generating the data set to fine tune from in the first place. But we want to leave that out and give our LLMs either the original Llama 2 that we downloaded the weights for, or the one with our adapter installed, a chance to fill out the rest of that. So we can see that's what it looks like. It has instruction, input, output, and we've combined those into this singular text field. Now we load our model, we set up our quantization, we load in the PEFT adapter, we attach it to the model, and then here we set the quantization settings and then load in the original Llama 2 7B model. So if you look more closely at the code here, we set up this here. So where we say model from pre-trained config.base model name or path, theoretically that would also refer to the Llama 7B base model. But once we install the adapter, it no longer does. So if you try to get the result from this model object and also the result from this trained model object, they'll be the same because we loaded the PEFT adapter over top of it. Even this model variable has changed to refer to that. So instead, we load in the Llama 2 7B again from scratch, even though we loaded it and put the adapter on before. And I think this took up like 12 to 15 gigs of VRAM to have them both loaded. Something like that. Okay, so we load in the model.
Just a reminder to the listeners, you essentially were able to also use your graphics card for some additional processing power in this?
Yeah, so, well, the models are running on the graphics card. We
Yeah.
set up here, we tell it to use a CUDA device if one's available. That means sort of an NVIDIA GPU.
Yeah.
And if one is not available, then you can use the CPU.
Great.
But that does mean that you can run out of VRAM on your GPU and not be able to load in the second model, theoretically, depending on how much RAM your graphics card has available. Okay, so what does the process look like? We, just as a test, we're taking our first row from our data set, and we need to use, so we're saying .2 CUDA here means that, load this, use the tokenizer also on the GPU. So potentially even more memory usage, but tokenizers are small compared to models. And then we're taking our text, in this case, that is that combined prompt, and getting it back as tensors to be used with the PyTorch model. And then we say model 1, which is our original model, .generate. We set a maximum number of new tokens to generate here. Things we don't set here are like temperature or things like that. So these are going to be deterministic outputs. And then we also generate an answer. So it's the same text. That's why we're using batch here. The same text, we generate a continuation using the original model. We generate a continuation using our fine-tuned model. We decode these back into text, and then we can see a response. So this won't actually run on Gitpod because it doesn't have GPUs attached or enough memory to load both the models in. But you can see, if I scroll up, so the original model, it says, read the instruction below and provide an answer. So that's the prompt we set up. And then our instruction from our original data set, the context from our original data set, and then it says response and prompts for response. Our original model, what it understands from this is that what comes next should be a bunch of section headers. So the original model is not instruction fine-tuned. It doesn't understand that when it sees an instruction, the correct response is to follow from that instruction, like follow the instruction, do what the instruction says. It follows from the instruction in the sense of generating a document that continues on from wherever previous document stopped. So we actually see a lot of these type of things in our data set, where the original model will generate, say, a list of references or a bunch of headers or say a blank space, and because it just doesn't understand the instruction following format. And so that goes back to something that I was talking about in our sort of first talk, where the thing that fine tuning is most useful for is getting it to understand language domain. So something like question answering or instruction following. The idea that in response to this, you are supposed to speak like this or do this thing, rather than sort of ensuring factuality. And then we put those responses back in the table. So this is our actual sort of code for doing that. We see we've generated these all in the same way, and then generated 2 responses, gone through all of our outputs, and uploaded them into the table. So actually, let's go look at that table now. So if you remember, we started out with our original table being Cassandra Link articles. So just an ID for the row and not getting the scroll to the right. But basically, all it contains is the article itself. It's split up because of limits with Astra, split up into a collection rather than just as a single text object, but that's all that's in this table. And then our original instructions table is basically our training data set. It has the instruction, input, and output, and reference to the original article ID. And that's it. So, and then in our test instructions, so we built the text object that is sort of the combined prompt for the fine-tuned or original LLMs, but we didn't actually store that in the table, only our outputs. So in the end, we end up with a lot of stuff in this table. So we still have the same instruction, input, and output columns, and the article ID. This we're going to talk about later, but the responses from the LLM are also stored in here. So the fine-tuned model gets us back the fine-tuned response. This is the one you just saw, where what's in the LLM response is just a bunch of headers. But you can also see this one has a reference to, I think this is an actual article on the DataStax docs. But if we were to look at the whole thing, it basically repeats that reference over and over again. Like it goes down the list, it says references 1, references 2, references 3, but they're all linking to the same article, and it hasn't actually done the instruction here, which is to explain the key factors to consider. Okay, so that's how we got our LLM responses into Astra for further evaluation. And then this is the file that we had just looked at before, that actually does the LLM evaluation of that data. There's also this human eval out of 10, which loads in the responses, shows them to the user, and asks for a rating. So you can see here, this is what that looks like. read each of the following. Instruction, explain the features of NoSQL technologies, particularly focusing on Cassandra's architecture benefits. And then it gives us this context, which is adapted from one of the articles. And then we can see this is scrambled. So it's not like response 1 is not always the original LLM, and response 2 is not always the fine-tuned LLM. In this case, response 1 is probably the fine-tuned LLM because it's giving a cohesive paragraph that is answering the question. And option 2 is giving a list of references, and, like this is an article that someone has published, links to GitHub repos for follows and stars. So you can see the original, well, this is almost certainly the original model. It has trouble following the instruction that's laid out in the prompt, whereas our fine-tuned model understands that format and does its best to answer the question. This doesn't necessarily always result in a better answer. So the way that our data kind of works, sometimes so the fine-tuned model has sort of learned that it should be sort of a succinct paragraph. So they're all sort of like this, that it's, one paragraph of text, pulls from the context, and no extra random formatting. But that can result in a situation where your original LLM will do something similar to this. It will follow the instruction, figure out how to do that, and then also include a references section underneath, which is something that could potentially push the rating of this, the original LLM response up past our fine-tuned model's response, in terms of, rating them as better or worse.
And just to confirm, sort of link back, this instruction set is something that is industry standard that we just defined, where there is the instruction, the context, and the response as the sort of three pieces of it. Is that right?
Yes. So in terms of sort of the format for instruction tuning data sets, this is standard. But this actual data set is generated from our own documents using GPT-4. So it put them into that same format. But depending on how you build your prompts, because in the end, what went into the fine tuning was a single block of text, so these sections just determine how you build that block of text in the end. So you don't have to rigidly follow this format necessarily if you're doing instruction fine tuning. You just need to be able to build a prompt where there is an instruction and then some text following that instruction, and then you can feed that to the model and do instruction fine tuning. Okay, so our LLM eval, we load in our data just like normal. When we create the prompts here, we're creating two. One is everything combined, the original response. So not the response from the original data set, but the response from the original LLM and the response from the fine-tuned LLM. They're all combined into a prompt. And then we sort of ask, how well does this follow the instruction? We looked at this file that's the instruction prompts. I was thinking of evaluation prompts. We would just say, you rate how well a given response by an examinee follows the corresponding instruction. What we actually ask is, how well does this response answer the original instruction? But we have some caveats in the system prompt. Rate responses in numbers from 0 to 9. Responses that directly reference the provided context rate higher than those that don't. Responses that are factually correct rate higher than those that are not. And you could fill this out with any number of evaluation metrics. You can't be 100% sure that they're being followed, which is why it's important to look at least a few of your outputs, look at the reasoning. But what our LLM eval actually does is combine everything into a prompt. So with the original question, with the question, and then also with the instruction, the context, and the output, and you ask, how well does this follow? Please give me a number from 0 to 9. And then you basically you set up your two data sets, one for the original LLM, one for the fine-tuned LLM, and you ask GPT 3.5. And in this case, we just cut off everything except that first digit, and then put it back in the table. So that's why when we were looking here earlier, we had these two columns, fine-tuned response and original response, that are just ratings out of 10. And, we can see confirmed our biases here where the original response, there are 0 ratings here where it clearly did not follow the instruction. You can see it's just asking back the same questions. This isn't really the instruction that it was meant to do. It was supposed to be providing practical advice, but instead we got back a list of questions. And in this one, because of what we're using to sort of parse the output, there was nothing at all to actually analyze. So, you get to 0 in that case. And then we have our own human evaluated instructions. And now onto the data analysis. I've set everything up right. Oh yeah, I had mentioned sort of the GPT-4 research page. So the way that they do our evaluation, they have exam results for the simulated exams. They have a bunch of benchmarks that they subjected it to. They have visual examinations specifically. So this is something that GPT-3 would not have been able to do because it's not a visual model. And even when they did the benchmarks here, they compared, or no, not these benchmarks. There's one table here where performance of GPT-4 with vision was compared to performance of GPT-4 without vision. Oh, it was this main one here. So you can see up at the top, GPT-4 subjects to all of the tests. So this is with vision, in the sense that if there are figures and stuff, GPT-4 is able to analyze visual content. You could use GPT-4 with vision turned off. No longer a multimodal model, just text only. And GPT 3.5 is text only. It doesn't really understand images. But benchmarks and then their vision benchmarks, which sort of come from a different, it's about understanding diagrams, it's about understanding charts, et cetera, and how well GPT-4 compares to that, and how well, so you can see that there's a big blank in the middle. So that means that maybe some of the standard state-of-the-art models that they want to compare it to don't do few-shot prompting. Yeah. So our responses that we have are GPT-4 with few-shot prompting, whatever state-of-the-art models they could get to work with few-shot prompting, and then state-of-the-art one-shot prompting. And then some of the statistical measures that we learned about are included in Hugging Face's evaluate. We use that later on to run rogue on our summarization data. Side note, Hugging Face somehow managed to get all of the most succinct Python package names. Like they own data sets, they own transformers, they own evaluate. Someone's really on the ball there.
Awesome.
Okay, back to our actual data. So we're loading in all of our data. This time that includes the ratings. So 0 to 9 ratings. And then we also load in our human evaluation files because we're going to analyze them alongside one another. So all the columns in our data frame, or So right now we're working in a data frame. But we've loaded basically everything in as pandas objects, which are basically strings. We want to turn the ratings into actual integers so that we can compare them, do math with them, average them, etc. And then we start plotting stuff. So first is our bar chart. It's not really, legible straight off, but you can sort of see that, the sort of orange responses, there are a lot lower ones and some higher ones, but the fine-tuned responses generally hovering around 7 pretty much everywhere. And we'll see that maybe fine-tune out when we look at the averages later. And then we have our box plot to show the mean and standard deviation. So you can see 1 is our fine-tuned model, 2 is our original model. You can see not only is it like the average is higher from where the orange lines are, the standard deviation is also much smaller. So they're more tightly clustered around 7. And then doing the actual math on them.
So another way to say that, we're getting better responses and more consistent responses.
Yes. So our original rating for these outputs was a 5.7 with a standard deviation of 1.9. And our fine-tuned rating is a 6.8, the standard deviation of 1. So the sort of largest group of responses, standard deviation is something like a third. I forget my sort of bell graph statistical knowledge, but basically the like most the largest group of responses are sort of in the original rating clustered between like 4 and 8, whereas the fine-tuned rating is hovering around 7 down to 6 up to 8. And here we use group by to do some aggregations. We group them by instruction type and calculate those same metrics. So we can see that for the means, our fine-tuned responses on, so just as a reminder, the instruction prompts look like this. 1 is summarize a section of the article. 2 is describe or summarize the impact. 3 is explain caveats, clarify configuration options, explain or summarize a feature, explain the technical concept, analyze and summarize a code example, compare and contrast two entities, provide practical advice, summarize the impact. I guess we did that one twice. Describe integration impacts, describe compatible technologies, describe a practical use case, or help me implement this. So we can see that the sort of means of these are increasing on the fine-tuned model, even for the individual prompts. So we go from a 6.1 on summarize the article to a 6.8. Or we go from a 7.6 on 10 was summarize the impact to a 9. And this has zero has zero standard deviation because every single example of our number 10 prompt got a 9 using the fine-tuned response. But you can see that generally we're sort of increasing the scores on every individual prompt and decreasing the standard deviation. So on each individual prompt that we trained on, we're getting better performance and more consistent performance. And then looking at our human-generated data, we can see, so our averages for the original were 4.04 and 4.21, and our averages for the fine-tuned model 6.87, 6.9, and 6.6, with larger standard deviations on the original, smaller standard deviations on the fine-tuned model. But basically, the LLM is reflecting back these sort of, feelings that we get from looking at some of the data. And then lastly, we can look at one of our statistical measures and see how that works in comparison. So we use evaluate.load_rogue to load in the test. What rogue does, like I mentioned before, is it compares your model predictions or model summarizations to a reference summarization. So generated from the same document, it compares. Basically, rogue is a measure of how many of the words in your reference summarization end up in your model generated summarizations. So it's literally a measure of like the similarity of them, but it's an objective number. Like if you run the rogue again with the same reference summaries and the same generated summaries, you're going to get the same answer. So our original rogue results give us a rogue score of 0.28 on our original model summaries. Rogue 2 gives us 0.129. And then our fine-tuned model goes up from sort of 0.3 to 0.45. Rogue is a scale from 0 to 1. If all of the words are exactly the same, you get a 1.0. So we can see sort of our model improvement here as the numbers go up for our summarization tasks. I had actually implemented this wrongly before, comparing the model generated summaries to the original article. And that showed us as getting worse because, well, neither of the model generated summaries are generated directly from that article. They are generated based on the context provided, which is also generated by an LLM. But in the end, the statistical measures bear out that our fine-tuned model is better. The human evaluation bears out that our fine-tuned model is better. And the LLM evaluation bears out that our fine-tuned model is better. So something that I wanted to potentially talk about because we didn't apply any benchmarks. We don't know for sure if we've avoided catastrophic forgetting. This is something I mentioned where it's basically the same as overfitting, where your model loses performance on new data because it's matching too correctly to your training data or your fine-tuning instructions. And benchmarks would potentially let us diagnose that because we would see that our fine-tuned model has dropped off in certain areas as compared to the original Llama 2 model, even though we have sort of shown that it's improved at instruction following with our human evaluation and LLM evaluation.
I gotta say, that outcome feels pretty great.
Yes. So
To
there was a time where, like I had mentioned, doing this fine-tuning evaluation,
mhm.
that even though we've loaded in the model, we have an original like model object, and then we also have a PEFT model object here, model trained model. There was the time here where I was trying to use this as the original LLM and this as the fine-tuned model. But it's the same object, so they generated the same response.
Yep.
So I was like panicking. I was like, why aren't we getting performance
Like forget
improvements?
about like any change. Why aren't we seeing any difference?
Yes, but
That's great. I mean, it just goes to show like coding and data engineering still matters
yeah.
in the LLM world. Speaking of, I wanted to check in and see what you thought could have been or like would be a next step, taking this and making it a little more. I was specifically curious about whether there was some like maybe some, I don't know, some data engineering or some like sort of refinement of prompts or of outputs that you thought might have been helpful here.
So like in terms of the evaluation, uh, yeah, I feel like there's potentially more to do with the evaluation prompts.
Mhm.
So maybe if we have people do comparative analysis, you know how our human evaluation asks the person to give two ratings. If it asks them to sort of rate one over the other, choose the better one and explain why, we could then use that to improve our evaluation prompts here so as to sort of what makes one response better than the other and sort of refine that in our prompts here.
Yeah. Um, do you think there could potentially be some like value before we get to this stage at assessing the output of some of the previous work we did, to sort of recognize which like prompts are better or which responses are have the best formation and maybe like filter down to just using those? Or do you
So
think
you
that's a
mean,
piece
well,
of the evaluation too?
yeah, so I think part of what we want to notice here is that our fine-tuned model is responding better in terms of formatting
Mhm.
to instruction prompts, that it is following the instruction and not doing something else.
Yeah, that is
And I
pretty
think
important.
that's important to sort of capture. So I wouldn't necessarily see cutting those examples out of the data set
Yeah,
as advantageous.
yeah. Okay, great. Um, So I know we talked about this a little bit this week, but I was curious as to your thoughts. One of the things we had discussed doing next was comparing the performance of this fine-tuned LLM versus a RAG chatbot. That was an interesting piece of the discussion from last week. Is there anything you'd like to add to that to sort of give our listeners, our watchers a teaser here?
Yeah, so this is a little bit of a repeat of something that I've sort of like mentioned a couple times, but never really gone into any in depth on. But fine tuning is good for, you know, the shape of your responses, the language used, the meaning of words, the sort of what the LLM considers to be next to be a sort of correct response, but
And
it
we
doesn't
definitely saw that.
ensure.
We saw the format of the response being just much better.
Yes, but it doesn't necessarily ensure factual correctness. Just because there was a lot of technical information about Cassandra in those original articles that were used to generate the fine tuning data doesn't mean it always answers Cassandra questions correctly. So, in terms of the ability to analyze things for factual correctness, I could see RAG being more efficient here. Just we spent, not only does it require a Google Colab notebook to sort of, run the fine tuning in the first place, um, and then to get all the responses for later evaluation, those are resources that RAG simply doesn't take. You set up, your similarity search index, and then you put the data in with your prompt, and you get back a response. So I think there is definitely some comparison to be made here. It's hard to know whether RAG will be able to overcome the formatting issue. Like if we give it factually correct information in order to follow the instructions with, but it does something other than follow the instructions, that's not really going to improve the score.
Yeah.
So
Yeah,
I
it
think
makes
there's
me wonder about
some interesting
doing
information to be gained there.
three sets. One that's RAG refined, one that's LLM refined, and one that's both. That's fine-tuned,
Yes.
and one that's
So
both.
I think one of the weird things about doing that is going to be the evaluation.
Mhm.
Like we trusted, in this case at least, GPT 3.5 to sort of rate we told it that factually correct responses should rate higher than incorrect responses. But does GPT 3.5 actually know any better
Mhm.
what a factual response is as compared to our Llama 2?
Yeah. Interesting. Interesting. Uh, okay, Obi, we are at very close to time here. Is there anything else that you'd like to add? Anything else you'd like to bring up here? I want to thank you so much for doing this talk. Yeah, please, the floor is yours.
Yeah. No, I believe that's everything I had.
All
Look
right,
forward
thank
to
you.
part 4 at some point in the future.
Absolutely. Hey, thank you, everyone. Have a great rest of your day, evening, night, whatever it may be, and we'll see you next time. Stream is over.